Have y'all ever heard what recursion is in some like forum discussion or some programming thing? Because it's often perceived as hard or difficult to learn and like there's like voodoo magic. But in this video, I'm going to teach you how to do some basic recursion. And at the end, we're going to make this pretty fractal tree that is only possible with the power of recursion. It's a great programming technique, basically just functions calling themselves. And it's very cool, very crucial for programming and just like game development and everything in general. So, if you enjoy the video, make sure to like and subscribe and comment any suggestions and or questions down below. So, let's get right into it and get recursion going. Okay, so let's make a script and get right into it. So I'm going to go into Surface Script Storage and make a script. Okay, so what is recursion? So recursion in its most basic form is almost like an iteration, like a for loop. So, you have a loop that, does something. I can type. There you go. So you have this for loop, and if you run it, it does exactly what you'd expect it to from 0 to 5. And you can replicate this using only functions. This uses a loop. So by doing that, you have a basic example of recursion. So recursion is when a function calls itself. So let's make a function, say local function recurse, and it's going to take in a I value. And then what we're going to do is we're going to print I and then call recurse I plus 1. So this does what this for loop does, except I would run it, but it would lead to an infinite loop, and it would give you a stack overflow because you run this function over and over and over and over again, and it would never stop. So it prints out I, and then it calls itself again. It starts from the top and just goes back and forth, almost like a loop. But like a for loop, you need a condition or you need like a stopping condition. And in a recursion, it's not like necessarily defined for you. So you have to define it for yourself. And usually that comes in the form of like an if statement at the beginning of the function. And in this case, we're going to say if I equals 5, we're going to just return. And so if I equals 5, then we're just going to return. So in that case, we won't actually reach the next recurse. So it'll call recurse, and then we'll go through, and then we will stop once I equals 5 because we won't be able to continue recursion. It cuts it off early. It returns and stops the flow, almost like a break statement in a while loop or a for loop. So we obviously have to call this. Unlike a loop, it doesn't just run on its own. Like this is a function, so you have to call it like a function. So we call recurse with a starting value of 0, and we should get nearly the same loop thing. Well, obviously, we have the old stuff that we did. Notice that this only goes to 4. That's just because I, botched the condition. With the for loop, it goes from 0 until I is less than or equal to 5. So this really should be if I is greater than 5, we return. So we get to less than or equal to 5. But whatever, it's good enough. So this is the most basic example of recursion. Now let's go for a little more complex of an example. So we're going to code a factorial. So a factorial is basically where you have a number, let's say 5, and so the factorial of 5, which is like 5 exclamation mark, would be 5 times 4 times 3 times 2 times 1. And that would give you the factorial, which should be 120. And that's what it is. That's the factorial of 5. And if you look at it, the factorial of 5 is 5 times 4 times 3 times 2 times 1. So this is almost the same as saying is 5 factorial equals 5 times 4 factorial, because it's 4 times 3 times 2 times 1. And actually that's how it is. Factorial is a recursive, like, math operator that you'll see in a little bit of calculus if you do that, like with Taylor series and stuff like that, and combinatorics and stuff like that. And it's actually very easy to implement with a recursive function. It would be, somewhat decently usable if you do it iteratively with a while loop or for loop. You can speak, but it's actually a lot easier to do it with recursion. So we're gonna say local function factorial. We're just gonna say fac. We're gonna take a number n, um, and this is going to have, two cases. So first we need the base case. What is this function gonna like stop on? That's the case of 0 factorial, because in math, 0 factorial is just defined as 1. So if n equals 0, then we're gonna return 1. So this function is actually just gonna be a recursive function that returns like recursive values. So then what we need to do is implement the next part, which is like returning like the actual recursive step. So the base case is this part up here. Now we need to do the recursive step, which is down here, where we're going to turn n times factorial of n minus 1. So what this is going to do is like just like our example here, 5 factorial. We plug in 5. Okay, it's not 0. We skip that. It's going to be 5 times 4, and it's going to go back up, and it's not that. It's not n equals 0. So it's going to be 4 times 3, and this goes 5 times 4, then 5 times 4 times 3, then 5 times 4 times 3 times 2, then yada, 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 until you get 0, which is going to give you 1, and then that propagates all the way back up. So you're multiplying your current iteration number times the next iteration of the recursive step. So if we print factorial of 5, we should, I did my stuff correctly, get 120. Indeed, we do. We get 120. So that is a simple factorial function for you. A good example of recursion in action in a problem that would be a lot harder to implement iteratively. So now let's bring our stuff that we've been doing on just like a normal script into the 3D, I guess 2D, with a fractal tree. So fractals are just like, a geometric shape that has like infinite like subdivisions. So this one starts at one branch, it branches to 2, that branch goes into 2 branches, then it goes like that. And recursion is perfectly situated to solve a problem like this. So we're going to try to replicate this. So first, we're going to need to create our part. I'm just going to make a normal basic part. We're going to make it looking square. That's good. Okay, that's 1 by 1. And then first we got to see where the front is. The front doesn't matter. We're going to set the orientation pivot. And we're just going to set the pivot. So go into model, then edit pivot. And we're going to move this guy back here. Actually, let's double check. 1 sec. Yeah, so actually we're going to make the front. So right click the block that you have, go show orientation indicator. See where this front faces. We want to make that the long part. Those make things easier down the road. There we go. We can make this like, I'm just gonna make this like length. There you go. Then we're going to edit our pivot. The pivot opposite of the front indicator at the back. There you go. So this is our little part, and you also want to make sure it's anchored. Anchored. There we go. So our part is done. Let's get rid of this stuff. So we're gonna make a function, call it branch. So we're gonna need function local branch because we're making a tree. Our recursive function is gonna be called branch because that's cute. And then we're going to take in a part and a depth. So the part is like the current part that we're recursing on. So if I go and look at this, you'll see that this is our first part, and then we'll have another part. And so we'll recurse on that because each one of these like little trees is like almost like a mini little subtree. They all go down to infinity, which is not good. Fractals are infinite. We don't want infinity. That's why we got this depth variable. It'll be incremented each like iteration we go down. We have to have like a max like depth. So I'm going to have a depth of 10. So I'm going to say local max depth equals 10. And then we're going to check if, so our base case is going to be if depth equals max depth. Max depth. Then we're just going to return. And then otherwise, we need to do the actual interesting stuff, which is the branching. So this is going to look a little weird, the for loop I'm going to use in here. But because I'm lazy and I don't want to type out 2 massive chunks for the left part and the right part, because they basically handle the same way. The only difference is the angle at which they're connected to their root. Like, look at here, you have, like, the root part here, the right part is the same length as the left part, it's, like, the same relative distance, whatever. The only difference is the angle. So, we're just gonna make a for loop. The for loop's gonna look kinda odd because we need, like, to go on, like, both sides. So, we're just say for I equals -1, 1, 2, do. So, this starts at -1 and has a iteration step of 2. So it's gonna start at -1 and then go to 1, and that's it. So it's just 2 iterations because that's all we need. And we're gonna say local branch part equals part clone. So we take this part from up here and we clone it. And then we need to actually, like, orient it according to our world. So we're gonna say branch part dot size equals a new size. So vector3 dot new, and we're gonna keep the part dot size dot x and the part dot size dot z, and then actually in the middle we're gonna put 1. So basically what this is gonna do, gonna keep the height the same, but we actually want to edit these depths, or the width and the length, I guess it would be, by a specific scale factor. So I'm gonna make a new constant at the top and call this local scale factor, and spell scale factor, and that is going to be equal to 0.7. So each iteration, we want the x size, which is the width, that will decrease by, that will, like, be scaled down by 30% because we're only taking 70% of it, and the z will be given the same treatment. So we're going to say, so the x is part dot size dot x times scale factor, and then part dot size dot z times scale factor. We're keeping one as a constant here because part dot size dot y is always one. We're going to leave it. You can always change that if you want it to be more adaptive to your situation, but this works out for me. The reason we have to make these actual, like, part things is because this part is not guaranteed to have a, like, width of 1 and a length of 4. It'll get smaller and smaller as it goes on, so we have to iterate on that recursively. And then, so we have the size done. Now let's change our pivot offset. So whenever you resize a part, the pivot offset actually does not adjust. We adjusted our pivot to be at the back of the part, right? But, like, when we resize it, it won't automatically change. And the editor does, which is kind of odd. But, like, for example, if I set it to, like, 2 or, like, 23, I guess, the pivot stays in the same spot, but the part still grows. We don't want that. We want the pivot to move, but we have to code that in. We're gonna say branch part dot pivot offset is equal to cframe dot new vector3 dot z axis times part dot size dot z times the scale factor times 0.5. So what this does is we basically say, okay, the z-axis just gives us a vector that is 0, 0, 1. Then we multiply it by the part dot size of z. Might be easier to group the 0.5 and the part dot size of z because we're just doing half of the z length times the scale factor. So basically, we're reusing this value up here, like the part dot size of z times scale factor, down here, and we're getting half of it because normally, like, the center of a part is, like, split down the middle. It's halfway. So when we scale it down, we're gonna crunch this side a little bit, and we want to go halfway there, but we don't want to go halfway to the original distance. We're gonna go halfway, like, the 70 or the 30% that we cut off. So it's gonna be like there. So we make the size, we scale it down, and then we go half of it, and that's how you get the new pivot. Because, you know, C-frame. I have more videos on C-frames and stuff on my channel. Just go check them out. They're pretty helpful. Now we are ready to do the pivot magic. New branch part pivot to art.cframe to world space. And we're actually going to give us some room here. We're going to say to world space cframe.new vector3 dot z-axis times negative part dot size dot z divided by 2. I guess times 0.5. Let's be consistent. We're gonna do times 0.5. And then we're going to do times keyframe dot angles 0 math dot rad 30 times I and then 0. So what we're doing here is we're going from local space to world space because every time it's like a rotation, so we got to keep it relative. So by going to from local space to world space, we're kind of like shifting everything. I have a video on world space and object space that you can check out as well. And what we're doing is we're just moving it to the edge of the part. So it'll move it like halfway like we're doing before. Um and then we're gonna like back it up like forward, like the same kind of style that we're changing the pivot offset. And that's because oh wait, I need to change my pivot too. There you go. Yeah, so we're just moving it up to the front of the part and rotating it by 30 degrees times I. So when I is equal to -1, it'll be -30, and that'll be +30, and that'll work out just fine. Now all we need to do is set branch part dot parent equal to workspace, and then call branch on our new branch part and depth +1. And this is all within the for loop. So we'll parent of the workspace and then call branch on the new part that we created, so it subdivides further, and we keep on going until we hit a max depth of 10. So let's run this. We don't get anything. Oh, that's because we never actually call branch. We have to start it off. So we call branch, stupid. We call branch on workspace.part. Because again, this is a function, you have to call it. So we call it on workspace.part with a depth of 1 to begin with. And we run it. And voila, we get our pretty little tree. And that is a very good use of recursion. So I'm sorry if I brushed over the C-frame stuff because that's not really the point of this tutorial. The point is to give you an introduction to recursion and talk about how it works, because this fractal is honestly like, it would be kind of hard to implement this with loops. I mean, it's just a way, way, way easier. Actually, I don't even know if it'd be possible to do it with loops, and probably would, but like still, it's way easier to use recursion because you start at a branch and you branch again, and you branch again. It keeps on branching because like each new branch is like a new mini subtree that you keep on going. And actually, this concept is very crucial in other like data structures like binary trees or whatever, because there actually are trees and you have to traverse them, and it's very easy to use recursion. So yeah, hope you enjoyed this quick little primer on recursion. If you want to see more like specific programming videos like these, let me know. I've been doing this in a lot of my classes recently, so I thought it would be cool to make a video on it and actually apply it in a Roblox using a beautiful little fractal. These are very useful for other game algorithms too, like the maze I made, the randomly generated maze that uses a recursive algorithm, and then other things as well. So I know some people want quad trees. I'll probably be doing that soon enough as well. That should be fun. But yeah, I'm glad to be back making videos for once. Don't know how consistent I'll be in the future, but I hope you enjoyed. Make sure to like and subscribe if you did, because your boy is gonna keep on making videos. I'm busy, but it'll come. Like, don't worry, I'll make more videos. But other than that, I hope you have a nice day, and goodbye.